In this video, I'm going to work through an example to demonstrate the difference between adjusted sums of squares and sequential sums of squares. So this is the Allen test dataset. So we have response variable ACL and three predictors. We have vocab, abstract, and SDMT. And we're just going to think about these so we can keep track of them as x1 as vocab, x2 is abstract, and x3 is SDMT. So I'll fit a multiple linear regression model. So ACL is our response, and vocab, abstract, and SDMT, x1, x2, and x3 are the predictors. And leaving everything at its default settings, in the analysis of variance table, it gives me adjusted sums of squares. And then the three predictors are listed here, vocab, abstract, and SDMT. So what are all these things? So let me annotate here so we can see exactly what they all are. So for the vocab row, so vocab was x1. So this is the regression sum of squares for x1 given the other two predictors in the model, x2 and x3. And then the row for abstract, abstract is x2. So it's the regression sum of squares for x2 given the other two predictors, x1 and x3. And then SDMT is x3. So this is the regression sum of squares for x3 given x1 and x2. Let's just tidy this up a little bit. Okay, so when you have adjusted sums of squares in the analysis of variance table, and you'll be able to tell because it'll label it ADJ, adjusted sum of squares, each row for each predictor is the regression sum of squares for that predictor given the other two predictors, or however many you've got in your model. So x1 given x2 and x3, and so on. Okay, so let's remember those numbers, 0.4381, 0.5230, 6.9132. Okay, and let me just clean this up. And I'm going to fit another model now with the same three predictors, but if I click the model button, I can change the order of the terms in the model. Okay, so let's suppose we're going to have SDMT be first in the model instead of vocab. Okay, so I'll OK that, and OK that. And now we have SDMT listed first in the analysis of variance table. SDMT and then vocab and then abstract. Okay, but if we look at the adjusted sums of squares, they're the same values we had before, 6.9132, 0.4381, and 0.5230. So actually nothing changes if we look at the analysis of variance table with adjusted sums of squares. And we can see that from the definitions, because this sum of squares here, 6.9132, is for SDMT, x3, given x1 and x2. And then this one, 0.4381, is vocab is x1, so that's the regression sum of squares for x1, given x2 and x3. And then 0.5230, abstract, x2, the regression sum of squares for x2, given x1 and x3. Okay, so if we change the order of the predictors and we have adjusted sum of squares in our analysis variance table, nothing really changes. But what happens if we have sequential sums of squares? Okay, so let me pull up the regression dialog again. And if I click options, where it says sum of squares for tests, it's currently set to adjusted, which is the default setting. And this is sometimes referred to as type 3. If I click that down button there, I can change it to sequential, which is sometimes called type 1. There is such a thing as a type 2 sum of squares, but that's something that's you're not given that option in Minitab, and it's not something we'll discuss in the class. So we'll use sequential sum of squares, and we'll OK that and OK that. And then you might have been able to see things change if you were looking very closely, but here we have sequential sum of squares instead of adjusted sum of squares, and the numbers changed. Actually, the first two changed, but the last one didn't. Okay, and we'll talk about that in a second. Okay, let me label these things so you know exactly what they are. Okay, so the first one, SDMT, is x3. So this is x3. This is the regression sum of squares for x3. Just by itself, that's it. Okay, not given anything. It's just the first predictor in the model gets to be by itself. Okay, and then the next one, so this is for vocab, which is x1. So this is for the regression sum of squares for x1 given whatever has been fit before vocab. So in this case, SDMT is the only predictor that was fit before vocab. And SDMT is x3. So this is the regression sum of squares for x1 given x3. And then this final one, abstract is x2. This is the regression sum of squares for x2 given everything else that's been fit already. So in this case, what have we got? SDMT, x3, and vocab, which was x1. Okay, so let me just tidy that up a little bit. Okay, so you can see how these sequential sums of squares are being built up. You start with the first predictor, SDMT, and then you add the second predictor, x1 in this case, vocab, given x3 is already in the model, and then finally x2 abstract, given that SDMT and vocab are already in the model. Okay, so something to notice here is look at that final predictor that was added to the model, abstract, x2 given x3 and x1. That's also the definition of the adjusted sum of squares for abstract in this 3 predictor model. Okay, and so that's why this number, 0.5230, is the same as the adjusted sum of squares for abstract. Okay, that's the only predictor for which the definitions line up. For the other 2 predictors, the definitions are different. Okay, the sequential sum of squares for SDMT is just for x3, and the sequential sum of squares for vocab here is for x1 given x3. Okay, so that's one thing to notice. And then the other thing to notice here is if I was to add 11.6799 plus 0.0979 plus 0.5230, add those 3 numbers up, I would get 12.3009. So for sequential sum of squares, if you add up the sequential sum of squares for each of the predictors in the model, you get the overall regression sum of squares, 12.3009. That relationship does not hold for adjusted sum of squares. So let me just demonstrate that. First of all, I'll just clean this up. And let's go back to the adjusted sum of squares table. If I can find it. There it is. Okay. I wanted the other one though, this one. Adjusted sum of squares with SDMT, vocab, and abstract. Okay, so here's the 0.5230. Remember, that's the same as the sequential sum of squares for the last predictor fit in the model. But what I'm wanting to demonstrate here is that if I add up the adjusted sum of squares, 6.9132, 0.4381, 0.5230, what am I going to get? I'm going to get something roughly around 8. Okay, it's not 12.3009. So for adjusted sum of squares, they do not have the property that when you add them together, you get the overall regression sum of squares. But that property does hold for sequential sum of squares. Just go back to the sequential sum of squares table. There we go. 11.6799 plus 0.0979 plus 0.5230. If you add those three numbers up, you will get 12.3009. Okay, so one final thing I'm going to demonstrate is, let's think about the regression sum of squares for, let's do x2, so abstract, given x1 and x3. Okay, so that is given by this number here, 0.5230. So the regression sum of squares for x2 given x1 and x3. So that's one way to obtain that number, is just by fitting the appropriate model where abstract is the third predictor fit after STMT and vocab, and just reading off the number here under the sequential sum of squares, or adjusted sum of squares in this case, they're both the same. Another way to calculate it is to fit two models and look at the difference in either the regression sum of squares or the error sum of squares. Okay, so which two models are we going to need? So we're trying to find the regression sum of squares for abstract given STMT and vocab. Okay, so the two models that we want to fit, well, one of them is this model. Okay, and the other one is the model that just has the predictors that are fit before abstract. Okay, so STMT and vocab. So let's fit that model. So let me think about this, STMT and vocab, STMT and vocab. So I want to get rid of abstract. Okay, and we'll okay that. Okay, so I'm going to write some things down here. So the regression sum of squares for this model with just these two predictors is 11.7778. So let me write that down. So SSR for STMT is x3 and vocab is x1. And we've got 11.7778. Okay, I'm also going to write down the SSE for this model. So the SSE is 31.2717. 31.2717. Okay, excellent. And let me go back to the three predictor model. Okay, STMT, vocab, and abstract, and I'm going to write down the regression sum of squares and the error sum of squares for this model. So SSR for x3, x1, x2 is 12.3009, and finally SSE for x3, x1, x2 is, where are we, 30.7487. Okay, now let me just clean that up. Excellent. Okay, now let me do some calculations now. So let me take the difference between the regression sum of squares for x3 and x1 and the regression sum of squares for x3, x1, and x2. Okay, so the difference between 11.778, 7778, and 12.3009. So I'm going to write that down. So 12.3009 minus 11.7778. So I'll do that calculation and I get 0.5231. 0.5231. Okay, excellent. And then I'm also going to do the difference between the error sum of squares for the two models. Okay, so 31.2717 and 30.7487. And if I do that calculation, I get 0.5230. Okay, so within round-off error, those two calculations give me the same thing. And what do they both give me? They both give me the regression sum of squares for x2 given x3 and x1. And you can see that it's this number here, 0.5230, within round-off error. Okay, this one was 0.5231 with the round-off error. Okay, so that's the other way to calculate a sequential sum of squares, is to fit two models and then look at the difference either in the regression sum of squares, the overall regression sum of squares, look at the difference in the error sum of squares. Okay, so what I would recommend is playing around with this example. Make sure that you can replicate all the calculations in these notes, and then make sure you understand the difference between sequential sum of squares and adjusted sum of squares. And there's a lot to think about here. So it's worth spending a bit of time just playing around with this example and making sure that you can fully understand exactly what's going on with all the different relationships between these different types of sums of squares.